Hey guys, hope you're doing well. Here we have the grade 12 physics paper 1 exam from November 2023. If you want to download the paper, just check the description below this video. A constant net force is applied to a block. Which one of the following statements is correct? Right, so what we have is a block. Now, let me talk you through a few scenarios. Let's say we have an applied force of 5 newtons and we have another force over here of 5 newtons. Then what would the net force be? Well, the net force would be 0 newtons. Okay? In that scenario, what would happen? Well, either block won't move, or if it is already moving, then it will continue to move at a constant velocity. Then will continue to move at constant velocity. That is all Newton's first law. Newton's first law tells us that if an object is acted upon by, there's no net force. If the net force acting on an object is 0, then the object will either remain stationary, so it won't move, or if it already was moving, then it will continue to move at a constant velocity. Okay, so it says that, but this is when you have a net force of 0, but we don't have a net force of 0 because they've told us that there is a constant net force that is being applied to this block. So that means that there is actually some force. Okay, so let's say, for example, we now have a situation where you've got an applied force of 5 newtons and you've got a friction force, for example, of 2 newtons. Well, then we know that in this scenario, the net force is 3 newtons to the right. And what we know is that if there is a net force, then the object will accelerate. Okay, so but once it's accelerating, it will accelerate at a constant acceleration. So it won't, let's say the acceleration is, let's say for example, the mass of this object is 1 kilogram. Then to work out the acceleration, you would say the net force equals to the mass times the acceleration, and the acceleration would be 3 meters per second to the right. So notice that the acceleration will remain a 3. Only if we change these values, then the acceleration would then the acceleration will change. But as long as these values stay the same, then that means this net force is going to stay the same. And that is what they are saying here, that we have a constant net force. So they're not going to change the net force. So can we see that the acceleration is going to be constant? And so we're going to take option B, constant acceleration. Some learners are going to choose this one, but read carefully. This one says that the acceleration is constantly going to be increasing, but that is not correct. The acceleration is going to be, in this example over here, we calculated it as 3 meters per second squared. So it won't change. A crate of mass m is stationary on a plane inclined at an angle theta with the horizon. Which one of the following statements regarding the magnitude of the frictional force on the crate is correct? Okay, so let's break this down a little bit. If we did a free body diagram, we know that we've got gravity perpendicular, we've got gravity parallel, which always acts down a slope. Okay, we would have some type of normal force, and friction. They said, oh yes, there would be friction. Okay, so now some learners are going to be confused with the friction, like where does it go? Well, what we need to understand is that this box is not moving. So what forces are trying to make it go down? Well, that is the gravity parallel. So friction is the force that is keeping it from sliding. So the friction is actually going to be acting up the slope like that. Because if the friction was also going in this direction, well, then obviously the box would move. But we know that it's not moving, so the friction is what's holding it up, okay? Because this parallel gravity is trying to make that box slide down the slope, but there is friction that is keeping it from moving. So let's see. The magnitude of the friction is equal to the component of the weight parallel to the plane. Yes, that is correct. These two have to be the same for this object to not move. Okay, so that is our answer. But let's just quickly see. The friction is larger than the weight parallel to the plane. No, it's not. Is equal to the weight perpendicular is larger than the perpendicular. No, none of those. A ball is projected vertically upwards from the top edge of a building. Point P, Q, R, and S represent different positions. Okay, so it goes from P up to Q, down to R, down to S. Ignore the effects of air friction. Between which 2 points will the ball undergo the greatest change in kinetic energy? Ooh, that's a good one. First thing we must understand is that kinetic energy has no direction. Okay, so for example, at P, the object is probably, let's say for example, the object is going up at 10 meters per second. That's its velocity. Just using an example. That means at point R, it would also be going 10 meters per second because it's got that equilibrium or that symmetry. Okay? At point Q, there would be 0. And then at point S, let's say it's 20. These are just example values, but they are pretty realistic. Okay? They would all make sense. So if we know that kinetic energy is half mv squared, we understand that the mass of the object is going to be exactly the same for all scenarios. So that's almost like a constant. So the only thing that will give us a big change in kinetic energy is when there's a big change in velocity. So from P to Q, or let's actually talk about this, from P and S, would be from 10 to 20. Don't say that this one is 10 up and this one is 20 down. So that actually means 30. That's not correct because with kinetic energy, direction does not come into account. Okay? Between P and R, that would be between 10 and 10. So that would not be anything. Because this, P and S was 20 minus 10. P and R was 10 minus 10. R and S, that would be 20 minus 10. And then Q and S would be 20 or 0 minus 20 or 20 minus 0. So look at that. That is where the biggest change is, from Q to S. So the answer is D. A ball is dropped from a height h, strikes the floor with a momentum of P, and then a ball is then dropped from a height of a half h. Okay, so it doesn't bounce up. It's two different scenarios. So a ball is dropped from a height h and strikes with momentum P. The ball is then dropped from a height of a half h, and they want to know, so they pretty much want to know, how does this momentum change with this momentum? So we know that momentum is equal to mass times velocity. So we know that the mass of both of these balls is the same. So the only thing that really changes the momentum is going to be the velocity. So if the velocity for this one is v, for example, then what would it be if it's a half the height? A lot of you are just going to automatically say that it's going to be a half of the velocity. Because it's got half the distance that it travels, it will only reach half the velocity. But that's not necessarily correct. We need to understand, how does velocity change with distance? So we know that there's this formula, which tells us how velocity is a function of distance. If you used any of these other formulas of equations of motion, or vertical projectile motion, then they all involve time. But in this question, we're not wanting to talk about time. Okay? So this formula here tells us nicely how velocity gets affected by displacement or distance. So if we take the square root, then what we can see is that it's got something to do with a square root. And so immediately you can actually just go for this answer over here. A box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Which one of the following combinations of forces do work on the box? Okay, so we know that work is equal to the force, whichever the force is, multiplied by the displacement, multiplied by the cos of theta. Now this theta, remember, is the angle between the force and the direction of motion. Okay, so let's say, for example, the box is moving in this direction. Okay, then look at this angle between P and the force. Can you see that that's 90 degrees? And can you see that R is also 90 degrees? The angle between the force and the direction of motion is 90. Even if I said that the object is moving to the left, can you see that that angle is still 90? Okay? Now, what you must understand is that then if you had to go put a 90 over here, we must understand that cos of 90 is 0. So this force and this force will have a work that'll be equal to 0, because this whole expression will be equal to 0. So P and R do no work, because they are at 90 degrees to the direction of the motion. However, S and Q will not have a 90 degrees. It'll have some type of angle. And so Q and S, for this part here, for Q and S, it won't be a 0, so they are doing work. And so B is the correct answer. They will do work, whereas P and R, they won't. A train moving at constant velocity towards a stationary listener emits sound waves at a constant frequency. Which one of the following statements about the sound waves observed by the listener is correct? Okay, so what we have is we have a person, okay, and then we have a train, okay. So here we have a train, and this train is moving at a constant velocity over here, and it's emitting sound waves. Okay, now what we must remember is that as this train is moving, because it is moving, it's going to compress these sound waves. It's going to cause these sound waves to get closer and closer to each other. It's going to squeeze them together. And so this person is going to hear, or they're going to observe, more waves arriving per second compared with what the train actually is releasing. So maybe the train's frequency is releasing a 50 hertz, whereas the person is hearing 80 hertz, because they are receiving more waves per second, because the train is almost squeezing the waves together. So the frequency is going to be higher than the emitted frequency. So that would be your answer. Refer to the diagram below. Q and R are small spheres suspended by light insulated strings. When a negatively charged rod is brought closer to sphere Q is repelled. Okay, so immediately, if this is negative and it causes this one to be repelled, then it means that this one must also have been originally negative. And when it's brought closer to R, then it's attracted. So that means R must originally have been positive. Which one of the following can be possible for the nature of the charges on sphere Q and R? Okay, so they don't have negative and positive, but it can't be A. They can't both be negative. It can't be B, because we said that Q can't be positive. Definitely can't be positive. So the correct answer is going to be D, but let me try to explain. We said that Q would have to be negative. That's why it moved away. So that's correct. And then neutral would still be okay for this one. Let's say it's just neutral. What that means is it has equal amounts of positives and negatives. So maybe it's got, maybe R has 3 positives and 3 negatives, but normally they would be scattered randomly. But what would then happen is that when this negative charge or this rod is brought closer, what would happen is that the negatives would want to move away, and then the positives would be attracted. And then this positive side could still attract over to that side over there. And so neutral is also going to work. And so the answer for this one would be D. You might be wondering, why can't C work? Well, C wouldn't work because if this one was neutral, if this one was also neutral, like that for example, then as soon as this came closer, then these positives, the positives would rearrange themselves to become on this side, to go on that side, and then the negatives would go on the other side, and then Q would actually be attracted instead of repelled. So we can't have it that this one is neutral. So the correct answer has to be D. 4 voltmeters, V1 up to V4, are connected as shown. Which voltmeters will have the same reading as V1 when the switch is open? Okay, so when the switch is open, there will be absolutely no current flowing in the circuit. So in this kind of scenario, it's only going to be the voltmeter that is connected across the switch. that will have the same reading as the voltmeter up here at the battery. Let me try to explain that. The way you can think of it as this voltmeter over here, on this side, it's connected to this side of the battery, and then on this side, it's connected up to here, up to where the switch is open. But that switch open is also connected to that same terminal over there. So both of these parts are connected to the same side of the battery, okay? And then if, for example, I look at this voltmeter over here, I can see that this side is connected to this part of the battery, and then this one is connected over here, but this part is still connected to that part of the battery. So this voltmeter is only connected to this one half, and this voltmeter is only connected to this one half. So you wouldn't notice a voltage drop. Whereas if we look at this switch, or this voltmeter, this side is connected to this, and this side is connected like that. And so you can see that it's connected across the battery instead of being connected only on one side. So the answer would be B. A split ring commutator connects the coil of a generator to an external circuit. Which one of the following combinations is correct for the magnitude of the induced current in the external circuit? Okay, so we know that when it's a split ring, we know that that's DC, which means constant. Okay, so we mean constant direction. So it can't be, for the direction, we can't say that it's the changing one. That would only be if we had an AC. But now if we remember the graph, or a typical graph of a DC, it doesn't just go like this, it goes like that, for example. So we can see that the value changes. You know, maybe this is 5 and maybe this is 10. So we know that the value changes, so the magnitude changes. So we can't choose any of those two. So the only answer then would have to be C. Light of a suitable frequency is shone onto the surface of a metal and electrons are ejected. Which one of the following is equal to the ratio of the work function to the threshold frequency? Well, we know that there's this formula in this chapter, right? Now that formula, I typically said that you would use that for the light. But what about the metal? Well, with the metal, we change the energy to work function, and we change the frequency to threshold frequency. So it says, which of the following is equal to the ratio of the work function to the threshold frequency? So the work function divided by the frequency, threshold frequency, what would you be left with? H, and that is called Planck's constant. Two blocks of mass 4 and 9 kilograms are connected by a string. The blocks are held at rest, which is inclined at an angle of 35. A constant force acting parallel is applied to block B as shown. The blocks now accelerate up the plane at 2 meters per second. Okay, so this part over here, up to there was no force. There was no force, F. Now, with this part, now we do have a force. And so in this one, there was no acceleration. But now in this new scenario, now there is an acceleration. Okay? First question says, state Newton's second law of motion in words. Newton's second law of motion all comes from this F net equals to ma, the second law specifically. And if you get the a by itself, you end up with F net over m. I will give you the definition now, but what it says is that when a net force acts on an object, the object will accelerate. This acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. Here is the proper definition from the memo. When a net force acts on an object, the object will accelerate in the direction of that force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. They tell us here that the kinetic friction force acting on blocks A and B is this and this respectively. When they use this word respectively, it means that A goes with the first one because that was the first letter, and then B goes with the second one. Okay? says, draw a labeled free body diagram showing all the forces acting on block A. Okay, so block A, have a look at it over here. We know that it's going to have gravity perpendicular, so we can say FG perpendicular. It's going to have a parallel, always acts down the slope, so that's always going to act down the slope. Okay, it's going to have a normal force, and then it's going to have friction. So we know that it's kinetic. So we know that the system is moving. So we know that it's not this part. We know that it's now this new part over here. Okay, so we know that we are moving up the slope. So if we're moving up the slope, then, because it says we accelerate up the plane, then it means that the friction force would always go in the opposite direction of movement. So there's your friction force. And then there's going to be a tension force in the string, which is trying to pull the box up that slope. There we go. Okay, so there's your 4 marks, because gravity parallel and gravity perpendicular, that's 1 mark. Then friction, 2 marks. Tension, 3 marks. Normal force, 4 marks. And obviously with these free body diagrams, there's different ways you can do this. You can, there's some learners don't like to put parallel gravity and perpendicular gravity. They just put one line down. Some learners don't like to use FG. They like to use W. So check the memo and you'll see what is allowed. They accept quite a bunch of different ways of doing it. Okay, it's not just one way only. Okay, so we've done this question. Now it says calculate the magnitude of the tension in the string. Okay, so let's just check. Could we get all of our answers from this question, from this one here? So we know that we're moving in this direction, so we could use F net equals to MA. It's not going to be a simultaneous equation because normally the unknowns are tension and acceleration, but they gave us acceleration. Now let's say up the slope is going to be our positive direction. So now you only need to look at the forces in the direction of the slope. So we're going to say T minus friction minus FG parallel equals to MA. See, I literally just took those forces over there. Okay, normal force and gravity perpendicular, they are in the complete opposite direction to the motion, so they don't come into the F net equals to MA. And so the tension force we don't know. The friction force for object A is 5.88. The parallel gravity is going to be, remember FG parallel is always mg sin theta. So that's going to be the mass times 9.8 times the sin of theta, which is 35. And that's going to be equal to mass times the acceleration, which is 2. Now you know how to get t by itself. If you had to eventually move everything over, you should get a value for t as 36.36 newtons. You don't need to give any direction. They also just said calculate the magnitude. Okay, now this tension force, remember, is the same tension force in the string. So it's the same for block A and it's the same for block B. Now they want us to calculate the force of F. So what we're going to go do now is we're going to now go work on this object over here, okay, block B. Please note, there is a way that some learners like to do this where they combine both of these into one system. You do get the right answer, but they are penalizing learners for doing that method now. I've checked on the memo. That method is no longer allowed in terms of they're not going to give you full marks for the question. So don't use the system approach where you think of all of these as one object. Keep it separate, okay? Okay, so we're going to do a quick free body diagram on object B. We know that there's a force pulling it up. We know that there's a tension force pulling it down. This tension force is trying to pull it down. We've got a normal force. We've got a perpendicular gravity. We've got a parallel gravity. And we've got a friction force. Okay, so if we use F net equals to MA, and we choose up the slope as positive, then it's going to be the force minus the friction, minus the tension, minus the FG parallel equals to MA. So the force, now this one's friction is 13.23. The tension we got from the previous one is 36.36. Okay, I'm going to run out of space here. So F minus the friction force of 13.23 minus the tension force of 36.36 minus the FG parallel, which is its mass, times gravity times sin 35 equals to its mass times the acceleration, which is 2. And if you just had to take all of these to the other side and get F by itself, you would eventually end up with 118.18 newtons. Okay, so moving now into here now, it says that the angle that the plane is now decreased. Okay, so they're going to decrease the angle. So maybe it's going to look like this now. So they're going to make this angle a little bit smaller. Now it says, how will this change the kinetic friction force acting on the block? Now when they say increase, decrease, or remains the same, don't just think about it and be like, I think it's going to decrease, or I think it's going to increase. No, you need to look at the formula. So we know that the formula for kinetic friction is the coefficient times by normal force. Now you can write normal force like that or like that. Now we know that the coefficient is dependent on the surface. Is it wood? Is it concrete? Is it rubber? They're talking about the surface between the object and the slope. Okay, so is that going to change? No, they are not changing the surfaces. They're just changing the angle. So this here is a constant. So we don't really need to worry about that. So then what we need to go and do is look at the normal force. Now remember, your normal force is the same as your perpendicular gravity. And we know that perpendicular gravity goes mg cos theta. So I'm going to do this question all in one go. So what you would do is you would go say that normal force is the same as Fg perpendicular, and we know that Fg perpendicular is mg cos theta, like we just said. So what we need to go and do is realize that this m value is not going to change because they're still going to keep it a 4 kilogram block. Gravity is not going to change. It's still going to be 9.8. However, this part over here is going to become the cos of a smaller angle. So for example, if you say cos 35, which is the original angle, that is 0.819. But if you say the cos of a smaller angle, let's say 20 degrees, for example, let's see what happens to cos. 0.939. So it actually becomes larger when we make the angle smaller. So we can then say that if theta is smaller, then cos theta is going to increase. So if that's going to increase, then it means that this entire parameter over here is going to increase, which means that this part over here is also going to increase. Okay, so you can just like explain that to them. So you could say, if theta is smaller, cos theta will increase. Therefore, Fg perpendicular will increase. Therefore, let's say therefore normal force will increase, and therefore kinetic friction will increase. Okay. Okay, for this question, I just want to remind you 3.4 will be on the next slide. Okay. A ball of mass 0.5 kilograms is thrown upwards from the top edge of a building, which is 15.3 meters high. The ball reaches a height of 5.89 above the top of the building. The ball strikes the ground, bounces upwards, reaching a maximum height at P. Ignore the effects of air friction. Define the term free fall. Okay, so we know that free fall is, for example, if you look at this ball when it's over here, for example, what are the forces acting on that ball? Well, the only force acting on that ball is gravity. There's no applied force. But then you're like, yeah, but Kevin, how did the ball end up getting thrown? How did the ball go upwards if there's no applied force? There was an applied force at this moment over here. But as soon as that applied force has happened, then as soon as the ball leaves the person's hand, then there is no longer an applied force. So when the ball is over here, 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 there is no other forces except gravity. And that is what free fall is. Free fall is when an object is moving under the influence of gravity only. And so here's the definition from the memo. It is motion under the influence of gravitational force only. And they said that they will also accept the word weight and gravity. So you could say it's motion under the influence of weight, or it's motion under the influence of gravity only. This question, using equations of motion, calculate the speed at which the ball was projected upwards. Okay, so very easy. We can just look from here up to here. Okay, so this is your initial position, your starting position, and this is your ending position. Some of you are like, Kevin, but the ending position is over here. Yes, but you can have a different starting and ending position depending on where in the question you are busy looking. Okay, so we've got these equations of motion. So let's see what information we have. We know that the displacement is 5.89. So we've got the displacement. Okay. Okay. Now, so we can't use this formula. Now, we know we know that at this point over here, we know that the velocity is 0. That would be your final velocity of 0. We know that whenever an object reaches its maximum height, it has a velocity of 0. So we have that. Okay, so then, and then we also have acceleration. We know that in this chapter, acceleration is always 9.8 downwards. So we have acceleration. Okay, and so there's acceleration. So pretty much we're not going to use this formula because we don't have time. So that one's out. I don't really use that one too often. That one's out. And so this is going to be the best formula to use. So let's go write that formula down. Choose a direction as positive. Doesn't really matter. I'm going to choose upwards as positive. And so we know the final velocity is 0. The initial velocity is what we are trying to find. If we choose upwards as positive, we know that gravity is always trying to make the object go down. If you throw a ball up in the air, the ball's always going to come down. So if you choose upwards as positive, then this must be negative because acceleration always acts down, which is the opposite of up. Now the displacement, we chose upwards as positive, and this point over here is above the starting position. So up goes with above, so that we can make this a positive value. And then you're just going to get this by itself. You can do that by just bringing all of this over to the left-hand side, and so you would end up with that over there, because this negative would have made this, yeah, let me just show you what I mean here. So, okay, no, let me not confuse you guys. Let's put this as a negative again. So when you bring this over, technically it would actually look like this. I just made this whole term negative, but now this negative and this negative is going to make a positive, and so you just end up with that. Okay, and then you can go type all of this in your calculator, then you can take the square root, and that is going to give us 10.74. 10.74. So we can say 10.74 meters per second. I'm not going to say up or down because they just said calculate the speed. They didn't say velocity, and speed is a scalar. Scalar does not have direction. So the answer is 10.74 meters per second. After the collision with the ground, the ball leaves the ground with a speed of 11.92. Okay, so we know that this ball is going to go, we know it's going to go up. We know that it's got a velocity now of 10.74 at the beginning. Then it's going to come down, and it's going to hit the ground over here at a certain velocity. And then they said it's going to bounce upwards with 11.92. So it's going to bounce upwards with 11.92 meters per second. Okay, so the first question over here says, calculate the amount of kinetic energy that is lost. Okay, that's very easy. In order to be able to count or calculate the amount of kinetic energy that was lost, we need to be able to know how much kinetic energy did it have as it hit the ground. I will call that position 1. And then we need to know how much kinetic energy does it have when it leaves the ground, which I'll call position number 2. So at position number 1, we know that kinetic energy is a half mv squared. So we have the mass of the ball. They gave that to us over here. But we don't know what is the velocity when the ball hits the ground. Okay, so we need to calculate what is the velocity when the ball hits the ground. Okay, now there's many ways that you can do this question. A lot of learners, I think what they're going to do is they're going to take this as the starting position up here. They're going to take this as the starting position, and then they're going to add these two numbers together, and that'll give you the total distance from the top to the bottom. And then you could easily just go and use, for example, you could use this equation over here. Other learners, what you guys will do is you will still use this as your starting position. And then you can also use this formula over here, but then you're just going to use 15.3 for your displacement. Okay, so there's different ways of doing this one. So I'm just going to do what I think most learners would do, and that is that they're going to let this be the starting position, and then this down here would be the ending position. Okay, and so we're going to use this formula. Now, a lot of learners think that because in the previous question we chose upwards as positive, they just want to keep it like that. You can do that. But what I'm going to do is I'm going to choose for this specific question, I'm going to choose downwards as positive. Only reason is because we are going down, and it just makes things easier to understand. So we don't know what the final velocity is when it reaches the bottom over here. What is the initial velocity? Please don't use this one over here. If you are saying that you are going to look at the question from up at the top here, then you must remember that your velocity up at the top there is 0. Okay? But if you are a student that is using this as your starting position, then your initial velocity would be this one. Okay? And then your acceleration, because now we're choosing downwards as positive, and acceleration is downwards, we can just leave that as a positive over there. And then the displacement is just going to be this plus, sorry, not that one. The displacement is just going to be this number plus this number. So 5.89 plus 15.3. And if you had to now go work out your final velocity by taking the square root of all of this, you should get a final velocity down here at the bottom as 20.38 meters per second. Okay, so let's just quickly remind ourselves. So we know that the ball hits the ground, and we know that that velocity is 20.38. We know that it bounces up with 11.92, which is what they gave us over here. So we can now work out the kinetic energy over here by just using this formula. The mass is 0.5, and this is 0.1, and this is 0.2, and so the velocity is 20.38. Don't forget the square, and that'll give us 103.84. Now remember, kinetic energy is measured in joules, and it has no direction. So now what we need to do is go work out what is the kinetic energy when the ball leaves the ground. So now we know that it's got a different velocity, so we can go calculate that, and that's going to be mass of 0.5, velocity of 11.92, and that'll give us 35.52 joules. So now they want to know how much energy was lost. Well, this is how much kinetic energy there was, and now that's how much there's left. So the amount that is lost would just be 103.84 subtract 35.52, and that'll give 68.32 joules lost. Now, I checked on the memo. You don't have to get exactly this value. You can go check on the memo yourself, but you can get a whole range of values. Okay. Now, this question says, calculate the time taken for the ball to reach point P after leaving the ground. That is super easy, because all that we do now is we don't even need to know any of this other information. None of that is necessary. All that we need to know is that the ball leaves the ground with 11.92 meters per second. And we know that it's going to reach point P, which is its maximum height. So we just need to know that that is its maximum height. So we know then that the velocity there would be 0, because that always happens at a maximum height. And then this would be your initial position over here. So now what happens is that you're only looking at this area and this area. So let's go look at our formulas. And so we know the final velocity. We know the initial velocity, we know acceleration, and they're wanting us to calculate time. And so I'm going to use that formula. Now, because the motion is going upwards, I feel like choosing upwards as positive. But that's just because I feel like that. But you could definitely choose downwards as positive if you want. Now, I know the final velocity for this part from here to here. The final velocity is 0. The initial velocity is 11.92. The acceleration, I know that that is acting downwards, but I chose upwards as positive, so I will put a negative there. And then the time is what I'm looking for. I hope from this question that you're just understanding from all of these questions that you use these formulas at different stages in the question. There is no fixed starting point and there's no fixed ending point. You decide where the start and end is for each individual question. Okay. So so now what we're going to do is we're We're going to bring this 9.8, which is now negative, but we're going to bring it to the other side so it becomes a positive. We're then going to divide by we're going to divide by 9.8, and that'll give 1.22 seconds. 1.22 seconds. I was looking at the memo for this question, just coming back to this question. The memo gives 16 different ways that you can do that question. So there are so many different ways that you can do it, okay? So as long as you're getting to the right area of answer, that's perfectly fine. Okay, so now let's just try to summarize everything that we have so far. So we know that this velocity was 10.74, so 10.74. We know that the velocity here is 0. We know that it hit the ground at it bounced up at 11.92. Okay, so it bounces up at 11.92. It hits the ground at 20.38, so 20.38. And we know that this part over here, the amount of time, we just calculated as 1.22 seconds. 1.22 seconds. Okay, and these are all in meters per second. Okay, so I don't know what we're going to need for here, but it's important that we have all of that information filled in. The velocity time graph for the motion of the ball from the instant it is projected upwards from the top edge until it reaches point P. Okay, so this entire journey has been simplified over here. Write down the numerical values indicated by each of the following. Okay, so let's try to forget about this and let's just make sense of this over here. We know immediately that the original velocity over here when we first started was 10.74. So we know that that is 10.74. We know that the ball then goes upwards, and what happens to its velocity? As it goes upwards, its velocity becomes less, and eventually we said that the velocity becomes 0, so that would be this point over here. So let's put a nice little X over there, and that would be that point over there. Okay, now the ball starts going downwards. So they obviously chose upwards as positive, because you see all the parts here where the ball's going upwards, we can see that the Y values here are positive. All of a sudden, the Y values are now becoming negative. So this is the part where it's going down. So this part here, where it goes down, is going to be all of this. Boom, 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 up to there. We know that it hits the hits the ground at a velocity of 20.38. And then immediately it would start going upwards again. So if it's going upwards, then the velocity would be positive, because we just said that they chose positive as upwards. We know that that's what they chose. So that would be, when it's going upwards again, would be this part over here. So this part here must be 11.92. And then as the ball goes upwards, what happens to its velocity? It starts to decrease again, goes decrease, until eventually it reaches point P, where its velocity would become 0, which is going to be at this point over here again. And so that would be point P. Okay. So they said write down the value of K. Okay, so the value of K is 11.92 meters per second. Okay. The value of L is 10.74. 10.74 meters per second. And then what is time 2 minus time 1? So what is the time from when it hits the ground until it reaches point P again? Well, we calculated that. That was the 1.22 seconds. And so we can just say 1.22 seconds. So I don't want you to look at these graphs and be like, oh, look, the ball's going downwards over here. That's not what this graph means. What we realized, and what I want you to pause and think about, is that in this part over here, the ball is actually going upwards. Over here, the ball is going upwards. Because it goes from 10.74, which is where it started over here, and as it goes up, what happens to its velocity? Its velocity becomes less. That is what you are seeing over there. But this downwards line doesn't mean the ball is moving downwards. Okay, that's important. When it gets here, that's where the velocity is 0. And that's what we can see. It says that the velocity is 0. So that would be this position over here. What then happens is the ball starts going downwards again. It hadn't gone downwards before, but now it starts going downwards. So because upwards was chosen as positive for this graph, then immediately the velocities become negative. See that? That's why we are now looking at negative Y values. Negative Y values, negative Y values, negative Y values. until we get to the point when it hits the ground, and that is when the velocity is 20.38. Now, immediately as it hits the ground, it's going to bounce up, and we said upwards is positive, and that's why all of a sudden the graph is back up here again, because now it's a positive velocity. And how much was it bouncing up with? 11.92. Now, as it bounces up, what happens to its velocity? It becomes less, and that's why we can see these velocity values becoming less, 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 less. At point P, we know that the velocity is now 0, and that is why we are back on the x-axis at 0. Okay? A wooden trolley of mass 2.7 kilograms moves to the left with a constant velocity of 3 meters per second. A bullet of mass 0.03 is fired horizontally from the left. See diagram 1. Okay. The bullet strikes the trolley and comes to rest inside the trolley in 0.02 seconds. The average force exerted by the trolley on the bullet is 591 newtons. The bullet-trolley combination now moves to the right. Ignore all friction and rotation. Write down the first question. Write down the magnitude and direction of the average net force that the bullet exerts on the trolley. So Newton's third law tells us that if object A exerts a force on object B, then object B will exert a force on object A. The direction will just be different. So when this bullet hits this block, what do you think this block is going to do to the bullet? Is it going to try to push the bullet? Is it going to try to exert a force on the bullet in that direction? Or is it going to try to exert a force in that direction on the bullet? Well, obviously, it's going to make the bullet slow down. So it's going to exert a force in that direction. So in this direction will be the force of the trolley on the bullet. So then according to Newton's third law, then the force of the bullet on the trolley will be in the other direction. Force of bullet on trolley. So it says write down the magnitude of the force exerted by the bullet on the trolley. So we know that according to Newton's third law, the force is going to be exactly the same. So we're going to keep it as 591. But now instead of saying to the left, we're going to say to the right, because it's this one over here. Calculate the magnitude of the velocity with which the bullet strikes the trolley. Okay, so I don't think we're going to use not equations of motion. I don't think we're going to use the conservation of momentum for this question, because the reason is we don't know the velocity of the system after the collision, and we also don't know the velocity of the bullet, which is what they're wanting us to calculate. So they are two unknowns, so that equation is not going to work. So what I'm thinking of is they gave us the time and they've given us the force. So this formula over here, F net delta T equals to delta P, is probably going to be the best bet. Now, they're talking about the bullet, so let's do everything on the bullet. Okay, this is all about the bullet. So let's choose to the right as positive. So what force was exerted on the bullet? Well, there was a force of 591 newtons exerted on the bullet, but that was to the left. Okay, so you're going to put a minus over here. Don't just put a positive, because remember, if this question is all about the bullet, then they want to know what is the net force that was acting on the bullet, and we know that that was 591 to the left. So because we've chosen right as positive, you would make this a negative. Now the amount of time is 0.02. For this one here, you're going to say mvf minus mv initial, because that is what change in momentum is. Okay, now this is quite interesting. So obviously the mass of the bullet is 0.03. We don't know what its final velocity is. Some learners are going to say 0. And I understand why. It's because they say that the bullet is going to come to rest. But it's only going to come to rest inside the block. But if you are standing on the side of this scenario, the bullet is still going to be moving, because the block and bullet are still going to continue to move. So the absolute velocity of this bullet is not going to be 0. yes, it's not going to move inside the block, but it's still going to move relative to the Earth. Okay, so we can't put this as a 0. That would have caught a lot of learners. Now, the mass is 0.03. Now, we also don't know the original velocity of the bullet. So we have a little bit of an issue because we've got two unknowns. Okay, so we need another equation to help us. So what I think we could maybe do is we can go and use the same formula on the block. So let's use Fnet delta t equals delta p on the block. Now you can choose right as positive again, you can choose left as positive, it doesn't really matter. I'm going to choose to the right again. Okay, so what was the force? Now because this is for the block, the net force is what force was exerted on the block. And we know that was this one over here. It was 591 to the right. So because we chose right as positive, we can leave it as a positive. The time is 0.02. The mass is 2.7. The final velocity, we don't know. We don't know what this final velocity of this block is, but it's the same final velocity as this one over here. So we can call it VF and VF. You don't have to say VF1 and VF2. Okay, now for this part over here, you're obviously going to put the mass again. Now, what was the original velocity of the block? It was 3, but be careful. It was 3 to the left, but we chose right as positive, so you're going to put a negative 3 over there. Okay, now we can just go ahead and start simplifying this. So 591 times 0.02 is 11.82, 2.7 VF, and then this part will become a plus 8.1. Okay, now you're just going to get VF by itself, and you should eventually get 1.38. So VF is 1.38 meters per second, and we chose right as positive, and we're getting a positive answer, so that would be right. So that is the velocity of the block and the bullet after the collision. So 1.38. So I know the bullet is not moving, but that is just, it's not moving inside the block. But if you were standing on the side of this system, you would see the block and the bullet moving past you. So relative to the Earth, this bullet is also moving at 1.38. So we can now use that as the final velocity of the bullet as well, which is this part over here. So we can now come back to this equation, and then the only unknown is this one over here. So we can now start simplifying this. So if you type this on your calculator, it'll be negative 11.82 equals to 0.03. We know the final velocity now is 1.38. And we chose right as positive, and this is going to the right, so that's all good. We can keep it as a positive, and then we can do that. Okay, so I'm going to take this to the left, and then I'm just going to bring this over to the right, and then add all of this together. And pretty much if you get your final answer, guys, if you've gone ahead and you've solved everything, you should eventually get 395.38 meters per second. I'm not going to give a direction because they just said calculate the magnitude. They didn't say, when they say magnitude, it just means the value without the direction. Okay, this question over here says, state the principle of conservation of linear momentum in words. So you guys just need to know your definitions. I'll quickly put it on the screen. Okay, so there we have it. The total linear momentum in an isolated system is conserved or remains constant. They used to say in magnitude and direction, but I guess, yeah, it's becoming a lot more, they're becoming a bit more easy with this definition, so that's all that you need to say for that one. And then this last question, I think they made a mistake in this exam paper that year, because it says calculate the magnitude of the velocity of the bullet trolley combination after the collision. But we've already worked that out, and I looked on the memo, and even on the memo, they used the exact same method that I used. So it is for 4 marks, but trust me, there is a mistake here. So you could literally just put 1.38 meters per second to the right, and you could just say proven in 4.2. They definitely made a mistake there because, yeah, we had to get that value in this previous situation over there. Learners conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance that the trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy at A. The horizontal distance is then measured. Okay, so pretty much kinetic energy is just a half mv squared. So it's pretty much just relating to the velocity. So obviously, the larger the velocity over here, the longer the distance will be. That's all that they're actually showing, okay? You can see on this graph that when they gave an initial kinetic energy of 6, the trolley was able to travel 1.5 meters. When it was 12, the trolley was able to travel 3 meters, and when they gave it 18, the trolley was able to travel 4.5 meters. So that's pretty easy to understand. The experiment is repeated with the trolley, but at different initial kinetic energies. The results are shown. Ignore the rotational effects of the wheels of the trolley. So, first question. Draw a labeled free body diagram showing all the forces acting on the trolley during its motion after passing point A. So, after passing point A, there is no applied force. Remember, a learner pushes a trolley of unknown mass until it reaches point A. Then the learner would obviously let go, and that is why the trolley eventually comes to rest. So there is no applied force because we are looking at after it passes point A. So the only forces acting on it would be gravity. Okay. There would be a normal force from the surface acting upwards onto the trolley. And then there would be friction, which would always go in the opposite direction of motion. And that is why we get 3 marks, because we've got 1, 2, 3. Okay. This question says, name the independent variable. The independent variable is the variable changed by the student. So what is the student actually changing over here? They are changing the kinetic energy that this trolley has when it gets to point A. They are not changing the distance. The distance is changing because of the kinetic energy that is being changed. So the student, what are they actually changing physically? That is the kinetic energy. The kinetic energy of the trolley. At point A. 5.3 says, state the work energy theorem. So the work energy theorem is the W net is equal to delta EK. And so what it tells us is that the net work done on an object is equal to the change in the object's kinetic energy. This question for 6 marks says, calculate the mass of the trolley if the coefficient of kinetic friction is 0.18. Okay, so for this question, we're obviously going to use this equation over here. Now, we know that the kinetic energy, when it gets to the ending position, it's going to come to a rest. So we know that the final kinetic energy, we know that that'll be 0 because it's a half mv squared, and we know that your velocity would be 0. So we can then work out, because you need to decide, do you want to use the 6 and the 1.5? Do you want to use the 12 and the 3? Or do you want to use the 18 and the 4.5? It's completely up to you. It doesn't matter. I'm just going to use the 6 and the 1.5. So I know the initial kinetic energy, and I know the final kinetic energy. So if I say W net equals to the change in kinetic energy, I know that change means final minus initial. And so W net is going to be equal to the final kinetic energy minus the initial, which I'm using the 6, okay? And so W net is minus 6. But now what is W net? Well, W net is going to be all the different forces that we have in the direction of motion, but that is only friction. So we know that W net is only going to actually be the W due to friction. And we know that W is equal to the force times by the displacement times by the cos of theta. And so if we are looking at the W of friction, then we're going to use the force of friction and then the cos theta for the friction. And so I'm going to replace this with that. So I replace the WF with its formula. Okay. And now I know that friction is equal to the coefficient multiplied by normal force. So I could say coefficient multiplied by the normal force, multiplied by the displacement, which we do have, multiplied by the cos of theta, which will be easy to figure out, and then that's all going to be equal to -6. Okay, so the coefficient is 0.18. Normal force is normally just mass times gravity, but we don't know what the mass is, so we're just going to say mass times 9.8. We know the displacement is 1.5. Now, theta is the angle between the direction that the object is moving and the direction of the force that we are looking at. So we are looking at friction, so we know that friction acts in this direction. So that is a 180-degree difference. So we're going to say cos of 180, and that's equal to -6. And so I'm going to multiply these 4 parameters together so long, and that'll give us -2.646 m equals to -6. I'm then going to divide both sides by -2.646, and we should get 2.27 kilograms. An ambulance is moving away from a stationary listener with a constant velocity of 25 meters per second. The siren emits sound waves at a frequency of 550, but the listener detects a frequency of 512.64. Ignore the effects of wind. State the Doppler effect. Okay, so I'm just going to show you the definition. So it is the apparent change in observed or detected frequency as a result of the relative motion between a source and an observer. Okay, blah, 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 blah. So you just need to know your definitions. It says, use the given information to calculate the speed of sound in air. Very easy. So we know that the formula is to calculate the frequency of the listener, we've got the V plus minus VL over V plus minus VS times by the frequency of the source. Now, the golden rule is when objects move towards each other, then what do? We use a plus at the top and a minus at the bottom. When objects move away from each other, then what do? We use a minus at the top and a plus at the bottom. I'm talking about over here and over here. So they tell us that the siren or the ambulance is moving away. So we're definitely going to use this scenario. So we're going to put a minus at the top and a plus at the bottom. Okay, so what is the frequency that the listener hears? Well, that is this one over here, 0.64. Now, normally you would use 340 over here. But in this question, they're saying, what is the speed of sound in air? So clearly they not wanting us to just use that value that we normally do. So we're going to leave that as an unknown. What is the velocity of the listener? Well, the listener is stationary, so they're not moving. What is the velocity of the source? Well, that's 25. That's the ambulance. That's the place where the sound is coming from. And then what is the sound, the place, the ambulance itself? What frequency is it making? Well, it's making 550. Okay, now obviously you can't cancel these out because there's 2 terms at the bottom, and that would be pretty awkward if you canceled that out. Like, what would you do then? So V minus 0 is just V. Okay, so there's multiple ways you could do this. I'm going to how could we do this? What would be the nicest way of doing this? Okay, I'm going to multiply these two together because they're both next to each other, and then I'm going to multiply this part over to the left-hand side. So you're going to end up with that, and then that. Then I'm going to multiply the 512 into the bracket, so 512.64V plus, now I've got to multiply those two together, 12,816, thank you for it being a nice number, and then that's equal to 550V. Okay, so now you just got to get V by itself, so if you eventually do that, you should end up with V as 343.04 meters per second. Don't have to give a direction, they just asked for speed. So that's going to be 343.04 meters per second. Okay, moving on to here now. If the ambulance moves away from the stationary listener with a constant velocity that is greater than 25, how will each of the following change? Okay, so what they're saying is that they're going to drive away even faster. Okay, so they're going to increase this value over here. Right, so let's just quickly write our formula down. So we know that they're driving away, so we're going to put a minus at the top. Oh no, we actually said that it was v minus 0, so it's just v. But we know that that is 343. Let's just leave it as v for now. And then v plus. Now, let's put vs and then fs. Okay, so they're saying that they are going to increase this value. Okay, but that won't change what the siren does. The siren makes 550 no matter what. That won't change that won't change the speed of sound in air. That is a constant value for a specific scenario. Whether they drive faster or slower, sound moves through air at a certain speed based upon the environment that they are in, the temperature, the pressure of the air. It's got nothing to do with the speed that the vehicles are moving. If it did, then why do we always use 340 as our constant over here? You see, we normally just use 340 over here. It's got nothing to do with the speed at which the vehicles are moving. Okay, so let's see. How would it affect the speed of sound in air? Well, it won't affect the speed of... It won't at all. So we're just going to say remains the same. Remains. How will it affect the frequency of the sound waves emitted by the siren? Well, the siren is the siren. No matter whether it's moving fast or slow, the siren can make 550 hertz. That's the way that siren was designed. Now, what is going to happen to the frequency of the sound waves detected by the listener? Well, if the ambulance is driving away even faster, so you've got this random person over here. The ambulance didn't see them with their broken leg over here, and the ambulance is just driving away faster and faster now. So if that ambulance is driving away even faster, because they said here that the constant velocity, which is greater than 25. Now remember that here's your siren, bebop, over here, and those are creating sound waves that are hitting the person's ear. Okay? Now if the ambulance is going to drive even faster, then those sound waves are going to be pulled or dragged. So it's instead of it looking like this, it's going to rather look like these green ones. There's going to be greater spaces between them because as the ambulance drives away, it drags those sound waves along with it. So would there be more sound waves hitting the person's ear every second or less? There would be less. That means the frequency that the listener is going to hear is less. Frequency means how many waves are going to hit the person's ear per second. So because the ambulance is driving faster, there's going to be, because it's driving away from the person, it's going to drag the sound waves. So less sound waves are going to hit the person's ear. And so the frequency is going to become less. So we're going to say decreases over here. You could also use this formula if you wanted to. If you make this value larger, because it's the velocity of the source, which is the ambulance, then when you make a denominator larger, then you're going to end up making this value smaller. And so you're also going to end up with a decreases. Oh, I think over here at B, I was supposed to say remains the same. Remains. The spectrum of a distant star when viewed from the Earth is red shifted. Is the star moving away or towards the Earth? Okay, so this is that whole red shift, blue shift. Let's quickly talk about that. So let's say, for example, we have planet Earth. Okay, so this is planet Earth, and we've got a star. There's our star, and let's say this is the year 2000. Okay, now that star obviously releases light. That's why we see it. So that light travels to the Earth as a wave. And on the planet Earth, we have some instruments that can measure the frequency. So maybe the frequency is 2000 hertz, just as an example. Okay, now what we need to quickly understand is red and blue. So we know that the spectrum of light that we have on planet Earth goes red, orange, yellow, green, blue, indigo, violet. And what we must remember is that violet is high frequency, whereas red is low frequency. Okay, and so the frequency, as you go from red to violet, the frequency gets more and more and more. So if something is red shifted, then it means that the frequency is more towards the red side, so the frequency is becoming lower. So when it's red shifted, it means the frequency becoming less. And then if it was blue, sometimes they use the word blue shifted, then the frequency is becoming more. So what they mean is, let's say for example in 2024, we have a look at that same star from planet Earth. And let's say now that star, now we're measuring a frequency of 1,700. So notice that it was 2,000, now it's 1,700. So the frequency is becoming less. That is what we call a red shift. Now, if you think about the way that frequency works in the Doppler effect, like if you have an ambulance that is coming towards you, what happens to the frequency that you hear? Well, as something comes towards you, the frequency that you will hear increases, right? Because remember, if you have an ambulance and it's coming towards you, it's got these sound waves coming from the ambulance. And as it comes, this is the siren, by the way. This is the siren. And as the ambulance comes towards you, these sound waves become compressed, and so the frequency that you hear will be larger than the frequency of the siren itself. And if the ambulance was driving away from you, then the frequency becomes less. So when something is red shifted, it means the frequency is becoming less, as we can see here and here. The only way that the frequency can become less would be what? If the star is coming towards the Earth, or if the star is moving away. It would have to be because the star is moving away from Earth. If they said it was blue shifted, then we would say towards. So we are going to say away. Now it says use the Doppler effect to explain the question. So we could say something like a red shift implies that the frequency is becoming less. According to the Doppler effect, this can only happen, or let's say, that the observed frequency is becoming less. According to the Doppler effect, this can only happen if the star is moving away from the Earth. 2 point charges, A and B, each with a charge of 3 times 10 to the negative 9 are stationary on a horizontal surface. Point P is r meters away, blah, 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 blah. Describe an electric field. Well, an electric field, let's draw like a rectangle. So it's just a place. So let's say this is the field. It's just a place where an electrical object will experience some type of force. Okay, so here you've got a field, and if it's an electric field, then if you put some type of electrical charge over here, it will experience some type of electrical force. So the actual definition, or when they say describe, you can say the following. So there you can just say that it's a region or an area or a space in which an electric charge will experience a force. This question, draw the resultant field due to A and B. Okay, so what we must understand is that if you have a positive charge, then the lines go away. So you could show that with arrows going away. And then when something is a negative charge, then the lines or the arrows point, or they go towards the negative. Okay, so here we've got a positive and a positive. So the lines are going to be going away from both. So how does that work? Well, you've got A and you've got B, and we said that the lines are going to be going away. So you can't connect these, for example. So you can draw a line going out this way, a line going out that way, like that. And then, for example, like that, and like that. Then you can imagine there would have been a line going out of this one and a line going out of this one, but then the two positives here are going to like repel each other. So you're going to get something like this happening. So you're going to get a situation like this. Okay, and they're not going to mark you down on how many lines you have. They just don't want to see any lines crossing. They want to make sure the direction is the same. And yeah, so pretty much that's all that you would need to show. You could show more lines if you wanted to. Doesn't really matter. Okay, as long as you show that the arrows are pointing away like that. Now it says the magnitude of the net electric field. Okay, so that's not the electrostatic force, that is the electric field. Okay, you know from the formula E equals to kq over r squared. We're talking about that one. They're telling us at point P is going to be 27. Okay, and that is because of this one and this one. The overall effect is having 27. So this question for 5 marks, calculate the value of R. So what we need to understand is that we don't know what P is, but we know that P is just a random point, okay? So remember, if you go look at the definition of a point charge, we always assume that this one is positive. So what is A going to do to P? Is it going to pull P to the left? Or is it going to cause P to go to the right? Don't even look at B. Don't even worry about that right now. What is A going to do to P? Well, A is going to push P to the right because this one's positive, so they're going to repel. So A is going to push P to the right. So let's go calculate that. We know that the electric field, because of A on P, can be calculated using this formula. And remember, when you use this formula, the Q is the Q that is creating the field, and that's this one over here. And so that's going to be 9 times 10 to the 9, multiply by 3 times 10 to the 9, to the negative 9, sorry. And then the R is just an R, so we leave it like that. Now, we know that that is going to push to the right. We know that that's going to go right. Now, if we look at the electric field, because of, now you can ignore A. Now, if we look at the electric field of B on P, it's going to be 9 times 10 to the 9, multiply by 3 times 10 to the negative 9. But now the distance is going to be 2r squared. And if you look at this one, it's positive, and this one's positive. So that means B is going to push it to the left. We know that that's going to be left. Now this 27 over here, they haven't given us the direction. But you've got to think about this carefully. Which of these two, either A or B, which one is going to have the greatest impact on P? Look at the value of the charge. It's the same for both. So they have the same strength. However, look at the distance. We should understand that the one that is closest is going to have the greater impact, whereas this one is 2r away. So they have the same charge, but the distance is less. So can we agree that A is going to have the bigger impact on P? So that's going to be a stronger effect over here. So we should understand that the overall impact of A and B working on P is going to be 27 to the right, because this one is going to be able to push stronger compared with B trying to push to the left. So we should understand that this is to the right. So let's then say that the net electric field is going to be equal to, and let's choose to the right as positive. We can say that it's going to be because of the electric field of A on P minus the electric field of B on P. Why did I minus? Because B on P is acting to the left, but we've chosen right as positive. Now we just go fill everything in. So we know that this part over here is 27, and it is to the right. We know that this one can be replaced with this over here. By the way, if you multiply these two, it actually becomes really nice. It just becomes 27 over r squared minus, and then if you multiply these two, it also just becomes 27 over, now this will become 4r squared. There we go. Now we've just got an equation where you need a common denominator. So we could just make the common denominator 4r squared. So that means we would need to multiply this bottom piece by 4, and what you do to the bottom you have to do to the top. And then over here you would need to multiply this one by 4r squared, so we'd multiply this one by 4r squared, and then we'd multiply what you do to the bottom you have to do to the top. So I'm going to do it over there. It's just like earlier grades where we had to get a common denominator. Okay, so if you multiply these two together, you're going to get 108r squared. At the bottom you're going to have that. Over here you're going to have 108 over 4r squared. And then over here we're just going to have 27 over 4r squared. So now because we have an equation and all the denominators are the same, we can ignore them. And so now we just have 108r squared equals to 108 minus 27. And so 108r squared is equal to 81. We can then divide both sides by 108. And so r squared is going to be 3 over 4. And then normally we would say plus and minus, but r can't be a negative value, so we're just going to take the square root of 3 over 4. It's going to give you square root 3 over 2, but if you round that off, it's going to give you 0.87 meters. Okay, this last one says, calculate the magnitude of the net electrostatic force that an electron would experience at point P. It's only 3 marks. So we know that there's 2 formulas for electric field. The one goes like this, but then the other one goes like this. Now, when we use this one, this charge is the charge that creates the electric field. So it was this one and it was this one. But when you use this formula, which has a baby q or a small letter q, then this charge over here is the charge at the point. Okay, so what they're saying is that they are going to take an electron and they are going to put an electron over here. So we're going to put an electron over here. Okay, so then what we can do, we already know the electric field at this point. They already told us the magnitude of the electric field at point P is 27 Newton to the right. Okay, but now you got to be careful. We said it to the right, but that was only when we said that point P was positive. Remember that? Point P we assumed as positive. That's what we've been taught to do. A point charge, we always assume it's positive. But what do we know about an electron? An electron is negative. And so that's going to flip everything around. This one's all of a sudden going to attract, and this one's going to attract. And so what ends up happening is that this P, well, this 27 is actually going to end up becoming 27 to the left. Because it's an electron now, which is the opposite charge, it's negative. So now we know 27 left is going to go here. That's the electric field. We're going to calculate the force, and then we just need to know the charge at that point, which is the charge of an electron, and that is given to us on our formula sheet. Okay, so we could say 27 is equal to the force over. Now, when the charge of an electron, on the memo, you are allowed to, you can put the actual charge of an electron, which you get on your data table at the beginning, which they give you in your exam. The charge of an electron is negative 1.6 times 10 to the negative 19. But when you are using this formula, you typically don't put a negative, okay? But I checked on the memo. If you do, they don't penalize you, okay? Now, if you had to go and calculate the force now, you would simply take this part and multiply it up. And you should end up with a force of 4.32 times 10 to the negative 18 newtons. We don't need to give any direction because they said calculate the magnitude. Here we have an electricity question. So it says the circuit diagram below shows a battery with an EMF of 12 and an internal resistance of 0.5 connected to 3 resistors. First question, state Ohm's law. So Ohm's law, you know how we got I equals to V over R? You could use that one. You could use V equals to IR, or you could use R equals to V over I. Any 3 of these can be used to explain Ohm's law. Let me show you. So if you do this one, then, so let's just do that again. If you do this one, then you would use this one. The potential difference across a conductor is directly proportional to the current at a constant temperature. Okay? Then if you say you want to talk about current instead, then you can see that current is equal to the ratio of potential difference and resistance. So it says here the current is directly proportional to the potential difference. So when they say directly proportional, it means that if this one is at the top, this one's also at the top. Then if you want to talk about this one instead, where you talk about resistance, then we'll talk about the ratio of potential difference to current. Let me get a different color. Ratio of potential difference to current. So then you'd say the ratio of potential difference to current is constant provided the temperature remains the same. So any three of those works. You can just choose which one you want to use in your exam, and then just always write out the formula to help you remember what it's all about. Okay, so we chose one of those. Now it says switch S is closed. Okay, so switch S is closed. Calculate the total for 5 marks, the external resistance of the circuit. That's a nice easy one. So what we need to understand, okay, is where are the parallel parts. So let's say we start over here and we go around, round, 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 round. As soon as we get to a place where the branch or where there's a split, that is the start of a parallel there. So then I'm going to go like that and like that. Now this one just goes all the way to the end, whereas this one gets to another branch. You see how it's at another branch over here? So that becomes a new parallel part. So let's go like that, and there it comes together, and there it comes together. So now it's going to be back to the original pathway, which was green, and then those come back together, and now it's going to go back to yellow. Okay, so these two green pathways, they are in parallel with each other. But inside that, there's another parallel part over here. Okay, so we got to calculate the total resistance. So what I would say is let's work from the inside out. So let's go get this parallel combination first. So we know that for that blue one, let's do it in blue. We know that it's 1 over R1 plus 1 over R2. And so we could say 1 over R parallel is equal to 1 over 10 plus 1 over 10. And that's going to give us 2 over 10, and then you flip it upside down, so that's going to be 10 over 2, which is 5. Okay, so now we've done this one, it's 5. Okay, so you could almost imagine that this whole part here is just 5. So you could imagine what your circuit now looks like. Your circuit would now look something like this. You would have the EMF of the battery, you would have the internal resistor, you've now got this little resistor here, which is, let's go a little bit higher up. You've got this one here, which is 15, which is this one here. You've now still got this one over here, which is 10. And then what we've done is we've combined this into one resistor now, which is now 5. Okay? And, okay. So the next thing we can do now is realize that this was a green branch. Okay, that's not going to work. But you get the idea, and then let's just fix it up. Okay, so what we can do is realize that this branch here is in series now. That's all in series, right? This part here. So we can now combine those to become 15. 10 plus 5 is 15, because in series you just combine. And so that's what we now have in our circuit. So now we should remember that these two are now in parallel, so we need to go calculate them by saying 1 over 15 plus 1 over 15, and that's going to eventually, if you add those together and do the whole flippity flip thing, you're going to eventually get that parallel part is going to be 7.5 ohms. So all of this combined is 7.5 ohms, and that is the external circuit's resistance. Okay, so I hope you understood what I did there. So what I did is I started here, and I got that to become 5. Okay, so that was 5. So then you can imagine that we've just got one resistor here, and it says 5. Then these two were in series, so it was 5 plus 10, which is 15. And so then all we had, this entire branch, was then 15. Let's write that a bit better, 15 ohms. And then I took that, and I took this one, which were then in parallel, and combined them to get a total value of 7.5 as our total external resistance. Okay, the next question says, what is the reading on the ammeter? Okay, well this one's an easy one because we're just going to use this normal formula that we use. Because we have the EMF, we're looking for the current. So we have the EMF looking for the current. We have the external resistance. We've just worked it out. And then we have the internal resistance over here. So it's fantastic. So we can just say 12 equals to I, 7.5 plus 0.5. And so 12 is going to be equal to I multiplied by 8. And so if you had to get I by itself, you would eventually get 1.5 amps. Now it says, what is the power dissipated by resistor R3? Okay, so we know that there are multiple power formulas on our formula sheet. There's power equals to that, there's power equals to that, and then there's power equals to that. Okay, now if we think about what we have for this 15 ohm resistor, which is the one that they want, we have its resistance. So let's not use this one. Okay, the next thing we need to realize is to use this formula, you would need to know the current. Don't say the current's 1.5. That is the current in this main part of the circuit. Remember when I drew those colors just now? We had yellow up here and over here. That is the only place where that 1.5 is going to be valid. Okay, so what we could maybe do, I think let's not use this formula. I think it would be easier to try to work out the voltage of this part over here. Because what we can do is, we know that the EMF of a battery, we know that this one is 12 volts. And we know that that EMF is equal to I R plus R. But now if we had to go and multiply the I out, we could get that. Now we must remember that this part over here is your external voltage or your terminal voltage, whatever you want to call it, this part over here. Okay, and then this part over here is the voltage that is lost inside the battery because of this little resistor, and so that is your lost volts. Remember that your EMF is split up into your external voltage that actually gets used in the circuit itself, and then there's the part that gets wasted in the battery. Okay, so to work out this one, you would use IR, and we can easily work that out because we know the current going through this part of the battery. We know that that is 1.5 amps, and we know the resistor. So we could easily work out the lost volts. So we could say EMF is equal to the external voltage plus the lost volts, which is I times R. And so we could say 12 plus your current, which is 1.5, your internal resistance is 0.5. And if you had to then go work out your external voltage, you should eventually end up with 11.25. Okay, so that means the external voltage is 11.25. Now, and then the voltage inside here is 0.75. So where is that 11.25 going to be used? Well, that is used here in this parallel part because there is no other device over here, for example. So remember that voltage in parallel is the same. So it means that this voltage for this whole branch is going to be 11.25 volts. And it means that this voltage for this entire branch is going to be 11.25 volts. But now in this branch over here, there is only one device. So we can say that this 11.25 volts is going to be used up with that R3 over there. Whereas in this branch, the 11.25 is going to be split up with those devices over there. So, and then by the way, if there was another device over here, let's say there was another device that uses maybe 2 volts, then remember, this 11.25 volts, which is the external, you would have to first minus this 2 volts over here, and then you would only be left with 9.25 volts for each of these 2 branches. Remember that? Okay? But in this circuit, there is no other device on the outside of the circuit. And so that is why we can say that this full 11.25 is going to be used up. There will be 11.25 volts in this part and then 11.25 volts in this part over here. And so here we've got the voltage, and so this would be a nice formula to use now over here. So we could just say then that P is equal to V squared, which is going to be 11.25 squared, and then the resistance is 15. And if we calculate that, we are going to end up with 8.44 watts. Okay, 8.44 watts. Switch S is now opened. Okay, so if they open the switch, then it means that this part of the circuit is going to be completely taken out. Okay, so that part of the circuit is no longer relevant. So what's going to change? Well, this part stays the same, 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 and this part stays the same. This part, the ammeter reading, is no longer going to be 1.5. And remember, we worked out the external volts as 11.25. Well, that's no longer going to be valid either. Okay? So the only things that are still staying the same would be these kind of values. Okay? For example, if a battery has an EMF of 12, it's always going to have an EMF of 12. If it has an internal resistance of 0.5, you can't change that. So these things are all constant. Okay, but don't use the 11.25 and don't use the 1.5. So it says, if the resistance of the light bulb remains constant, which we know, how will the brightness of the bulb be affected? So here's the light bulb over here. Now we know that brightness, you can look at power, which has 3 formulas. Okay, we're not going to use this one because we already have the resistance. So let's use that to our advantage. We don't want to use this one because this formula doesn't use resistance. So we either need to, and remember the resistance is going to be 10, and it was already 10 up in the beginning here. So you could think of this part as like a constant variable. So the only thing we need to work out to be able to figure out if the brightness is going to go up or down is what happens to either this part or this part. Okay? So, do you remember how many volts were coming through this pathway when the switch was still closed? Do you remember it was 11.25? That is how many volts came through here, okay? Well, that is how many volts we had available for this part. So the volts through the parallel branch was 11.25, and this was originally. What we're going to try to do now is we're going to try to see is the amount of volts that are now going to be able to go through here, or the amount of volts available for this part of the circuit, is it going to be more or is it going to be less than 11.25? And from that we can draw up some really nice conclusions. Okay, so we know that this part of the branch or this part of the circuit has now been taken out. Okay? Did you know? So we've just taken this resistor out. So a lot of learners, they will say, because we have removed a resistor, the overall resistance in the circuit will become less. But that is actually not true. It depends how you remove the resistor. Are you removing a parallel resistor or are you removing a series resistor? When you remove a parallel resistor, which is this one over here, because remember this part is in parallel with this branch, when you remove that resistor, you actually make the overall circuit resistance become more. Let me explain. We must remember that more resistors added in parallel lower the overall resistance, right? That's something you should know by now. The more resistors you add that are in parallel, the lower the overall resistance in your circuit. So what is the opposite of that? The less resistors that you have in parallel, the higher the overall resistance of your circuit. So what have we just done? Originally, this electricity had, when it got to this part over here, it was able to split into two branches. Can you think of the way electricity flows? Wouldn't that make life easier for the electricity when it has two pathways to go? And that is what we are saying. The more resistors you add in parallel, the lower the resistance. What that means is the more pathways you provide for the electricity, the faster or the easier it is for the electricity to flow because there's less overall resistance. Okay? But now we have taken this part of the circuit out. This part of the circuit has been removed. So what is now happening is all of the electricity is now being forced in through this one pathway like that. That actually makes things more difficult for the electricity because now it has to all try get through one little pathway. It's like walking into a shopping center that only has one door. Wouldn't it be easier if there were two doors, because then things could flow a little bit better? There would be less resistance. So the point I'm trying to make is that by taking this resistor out, we have increased the total resistance in the circuit. Okay? That's the first thing you need to understand. And if you really wanted to check me on this, you could literally go and calculate what the overall resistance is for this entire circuit, and you would see that it's going to be more than this value over here. Okay, so by opening the switch, the total external resistance of the circuit increases. Okay, so you need to wrap your head around that. When you add or remove resistors in parallel, you need to think carefully about, does that actually increase or decrease the overall resistance? And as I said, if you want to quickly go calculate the overall resistance here, you're going to get an answer of 15, which is larger than this number. Okay. Now, if we look at this formula over here, and we just multiply the I in, then you must remember that this part here, once again, is your external voltage. And then this part over here, I'm just going to leave it like that. Okay. Now, we must understand that if we now go work out the V external, you're going to end up with EMF minus that. Now, if the total external resistance of a circuit becomes more, think about that. If the total circuit resistance becomes more, what does that do to the current in the circuit? What does resistance do to the current? Well, if the resistance goes up, then the current has to come down. Therefore, total circuit current will come, or let's just say will decrease. Okay, you could even go do a calculation if you really wanted to. You could go calculate this value. It would be less than 1.5. Okay, so now if you think about it, this value here is a constant, right? We said that was a 12. We've just said that this value is going to decrease. This value here is going to decrease. This value is a constant. Okay, so then what is going to happen to this value if you compare it to what it was originally? Well, this originally was a 12, and it's still a 12 because that doesn't change. This value was 0.5, it's still going to be 0.5, but this value is going to be less. So this value is going to be smaller, this part over here. And so you're going to be subtracting a smaller value from this number. And so what is going to happen to this part? You might need to pause and just think about this. But what you would understand is that your V external is going to be larger. It's going to be larger than originally. So this value, your external voltage, is going to be larger than it was when we had the switch closed. So you know how earlier we had 11.25 volts coming through here? Now all of a sudden we might have, for example, 11.5 volts coming through here. Okay? Or 11.5 volts available for this part of the circuit. So that means that this part here is going to have more volts available to use compared with the original circuit. Compared with the original situation. So we're going to have more volts available for this light bulb. I'm not saying that all of this volts gets used over here. We know that some of it gets used here, some of it gets used here, but because it's going to be a larger value available, this light bulb will have more volts than what it did in the original circuit when we had this closed. So from the formula P equals to V squared over R, if this part is a constant and this part is getting larger, then what would happen to this value? It must get larger. And so therefore the brightness of the bulb is actually going to increase. A simplified diagram of a DC electric motor is shown below. write down the name of component A. Okay, so that is going to be your, so it's specifically that little half ring over there. And so that's typically what we call our split ring commutator. Split. Remember, when it's DC, it's a split. Split ring commutator. State the energy conversion. Okay, so remember, when you have a generator, you are then going to be converting the mechanical to electrical. But when you have a motor, then you already have the electrical, but you're converting it to mechanical. So that's this one, okay, for the motor. Now, in which direction will the coil rotate? Choose from clockwise or anti-clockwise. So this is where you got to use, remember, when it's a motor, we use our left-hand rule. If it was a generator, you would use your right hand. Okay, so remember, your index finger, you're going to point that from north to south. So right now, take your left hand and point your index finger, which is your like pointy finger, the one that you would normally point with, point that from north to south. So you should be pointing from right to left in front of your screen right now. Then the current, the conventional current always goes from this longer one. So it goes like this, like this, like this, like this, and like that. But we want to, and then it would go up around like that, and then like that over there. So you can decide to focus in on this half of the branch or this half of the branch. I'm going to focus in on, let me just quickly draw this. I'm going to focus in on this part over here. So I know that the current is going into the page. So that is going to be my middle finger. My middle finger is now pointing into the page. Now, what is your thumb doing? Is your thumb going up or is your thumb pointing down? If you've done this correctly with your left hand, your thumb should be pointing up. So that means this part is going to be going up. And then if you had to do the left hand rule on the other side, you'd see that this part is going to be going down. So it says, in which direction will the coil rotate? So if you had to look at it from, if you had to stand over here and have a look, then this part, you would see this part's going up and then this part's going down. So that's going to create a clockwise rotation. So we would say clockwise. Now this one says, give two changes that can be made so that it can rotate faster. Well, there's a couple things we could do. We could use stronger magnets, okay? We could use a stronger battery, so that it creates a better current. So stronger battery. Or instead of using stronger magnets, like you can use stronger magnets, but you could also bring the magnets closer together. Another thing you could do is you could use more turns. Remember in the formula for this Faraday equation, one of the things we talk about is the number of turns. So you could have more coil wrapped around here. Okay, so you could use more coil. And yeah, that's pretty much the different things that we can do to make this thing rotate faster or to make it better. The circuit diagram below shows an electric kettle and a toaster connected to an AC source with an RMS voltage of 220. The ammeter, Okay, define the term root mean square current. Okay, so this is just one of those definitions. Okay, so there's the definition there. The root mean square current is the alternating current. We can see there's an alternating current that gives the same amount of energy as if it was a direct current. If that definition doesn't make sense to you, don't worry too much about it. It's not a very popular question that they ask, but yeah, it's just one of those definitions. I'm not going to go into the details of that one right now. It's not that popular. When the switch S1 is closed, okay, so S1 is closed and S2 is open, that means this part of the circuit is completely invalid. The maximum current in the circuit is 3.6. Calculate the root mean square. Okay, so that's very easy. We know that your IRMS is equal to your maximum current divided by the square root of 2. And that is taken straight from the formula sheet. So they're telling us that the maximum is 3.6 and the square root of 2. And so if you had to work this out, you get 2.55 amps. 2.55 amps. That's an easy 3 marks. 2.55 amps. This one says when switch S1 is open but switch S2 is closed. Okay, so now this part is completely invalid. The root mean square current in the circuit is 2.62. Calculate the energy consumed by the toaster in 2 minutes. Okay, so when they talk about energy, these are the energy formulas that we have. I wouldn't use this one. So, and then obviously these V's and I's are RMS. Okay, we don't use the maximum values with these types of calculations. So it says when the switch S1 is open and switch S2, we have a root mean, so we have a RMS current of 2.62. Okay, so we have the current. So let's not use this one. Okay. They tell us, okay, so we don't even know what the resistance of this toaster is. We have no resistance values, so let's not use anything with an R, so let's take that one out. So then this is going to be the one we're going to use here. So W is equal to VRMS times IRMS times the time. So we've got the time, we've got the IRMS, and we just need the voltage RMS. But remember that because this is the battery, and this is the only device in the circuit, then this 220 volts would also be this one. This would also be 220 volts, right? Because that's just how a circuit works. Whatever the battery supplies has to be used up in the circuit. And if this is the only device in the circuit, then this would have to be 220. And it is measured in RMS. So then we can literally just say W is equal to 220 multiplied by 2.62 multiplied by the time, which is 120 seconds, must be in seconds, and this will give us 69,168. Now this is energy, which is joules. Two small spheres, A and B, made of pure zinc are at rest. 0.1 meters apart on a wooden table. Sphere A is negatively charged. Okay, so sphere A is negatively charged, while sphere B is uncharged and fixed to the table. Okay, so this one cannot move. Right. High intensity ultraviolet light with a frequency is now shone continuously onto sphere B. The work function of zinc is 6.63 times 10 to the negative 19. Define the term work function. Okay, so remember, this is that whole section on photoelectric effect where you shine light onto a metal, and if the light has enough energy, it can actually remove electrons from the metal. So, how do you know if the light will be able to remove energy from the metal? Well, the light has to have more energy than the work function of that metal. The work function is the minimum energy needed to remove an electron from the surface of a metal. And so here it's the minimum energy. You don't have to say this part in bracket. It's the minimum energy that can eject electrons from a metal surface. Okay, now it says explain using a suitable calculation why the UV light will eject electrons from its surface. Okay, so we know that the high intensity light has this frequency. So we could quickly work out how much energy that is. We could quickly just go use this whole Planck's constant formula, and we could just see 6.63 times 10 to the negative 4 times by that frequency, and let's see what we get. So we get 1.8564 times 10 to the negative 17 joules. So that is the energy of the light. This is the energy of the light. Now, the work function of zinc is 6.63 times 10 to the negative 19. What that means is that if you want to remove electrons from zinc, the light has to have, or if you want to remove electrons from zinc, you need at least this amount of energy. But can you see that this number, which is the energy of the light, is a bigger number than this? So we could say 1.8564 times 10 to the negative 17 is bigger than 6.63 times 10 to the negative 19. So therefore, electrons will be ejected. Electrons will be ejected. Okay? Do you remember that, guys? Let me quickly remind you. If you have a metal surface, okay, it's got electrons. Then you've got light. So here is the light, and we're shining that light. The energy from the light was this part that I calculated over here. The work function is the energy that is needed to remove an electron. So if the energy of the light is big enough, meaning that it's more than this, then it will be able to remove electrons. Okay, that's what we're saying. Now, this question says sphere A carries a total charge of negative 5.4 times 10 to the negative 6 and requires a minimum force of this to move from rest. Calculate the minimum number of photons of UV light that must strike sphere B, which will cause sphere A to move from its rest position. Okay, so this is a crazy brilliant question. Okay, it's weird, but it's good. I will explain. So first of all, we would like sphere A to be able to move. They said for that to happen, you need this amount of force. So from Coulomb's law, we know that force is equal to K Q1 Q2 over R squared. So we know that the force we need is 0.027. We know that K is 9 times 10 to the 9. We know that this one's charge is 5.4. We don't put negatives. We don't know what B's charge is going to be. We know that at the moment B is uncharged. But we know that we're going to start shining UV light onto B. And as soon as we do that, we're going to start removing electrons from it. And it's going to start becoming positively charged. When it starts to become positively charged, it will start to attract this one over here. So at the moment, we don't know what that charge needs to be in order for it to start pulling A towards it. We don't know what that is. We know that the distance is 0.1, and we square. Now, you're just going to go calculate the charge of B. And if you go work out the charge of B, I ended up getting 5.56 times 10 to the negative 9 coulombs. So, guys, listen carefully. Remember that charge B is originally neutral. It doesn't have a charge. But what we're going to do is we're going to take UV light, and we're going to shine UV light onto this one. And so what will that do? It's going to cause electrons to be released. Remember, electrons are negative. So because negative electrons are going to be released from B, B is going to end up becoming positive. Okay? Because it's going to become positive, it's going to start to attract A. And that means A would eventually start moving. But for that to happen, the force has to be at least 0.027 as per what they've told us. And so we went and we did a calculation, and we were able to see what must this charge be so that that can start happening. So we need this charge B to become this. This is what its charge needs to become. So how many electrons do we have to release in order for its charge to become that? Remember that every single electron, one electron, has a charge of 1.6 times 10 to the negative 19. So every time an electron is released from B, its charge of B is going to go up by 1.6 times 10 to the negative 19. Because each time an electron is released, B is going to become more positively charged, and it will become more positively charged by exactly that amount over there. So we need to think about how many of these do we need until B gets to that. So what we could do is just divide those two numbers in order to see how many of these fit inside here. Okay, so we could say 5.56 times 10 to the negative 9 divided by the charge of a single electron, and that'll be 3.475 times 10 to the 10 electrons. Well, that is how many electrons need to be released. But remember that to be able to release one of those electrons, your light has to, every time, remember when I've showed you this before, remember in the light, there are these little packets, and each of those packets is called a photon. Each time a photon hits the metal, one electron gets released. So for one photon, one electron gets released. So if we just calculated that that's how many electrons need to be released, then we could also say that that is how many photons in the UV light we would need. And so the final answer is 3.475 times 10 to the 10 photons. A beam of white light is shone through a cold gas. The emerging light is dispersed, and a line spectrum is observed on a screen. Okay, so remember, if you have a gas, a cold gas, and then you shine light, remember what happens is that because this is a cold gas, all of the little atoms and things here, they are all at a what? A high energy or a low energy? A low energy. So when you shine light, remember that that light has different colors: red, orange, yellow, green, blue, indigo, violet. And as that light passes through the gas, it is going to provide some of the electrons enough energy to be able to jump up to higher energy levels. And then the light that comes through is the light that was not absorbed. So maybe, for example, we've got a bit of red and we've got a bit of blue. And maybe as it was going through, the blue was able to be absorbed. So then on the other side, you're not going to see blue. You're only going to see red. So we call this the absorption spectrum, because it shows us we are able to see which things were absorbed. So I'm not saying that the red was absorbed, I'm saying that the blue was absorbed. But by looking at this, I can see that the blue is missing, so I know that the blue was absorbed. So name the type of line spectrum that would be observed. That would be an absorption spectrum, because it shows us we are busy seeing which things got absorbed. Okay? And then it says, describe the spectrum from 10.2.1. Well, what you would see, remember you would have other colors. So maybe we would also have some green, and let's say the green didn't get absorbed, so we would see it over there. What would we see in the place of the blue? Well, because the blue was absorbed somewhere by one of these electrons, maybe the blue was used up by this one. Then in the place of blue, you're actually going to see no color. And remember, no color is black. Black is the absence of any color. And so how would you describe an absorption spectrum? You could say it shows the full rainbow of colors with black bands showing or indicating the colors that were absorbed. Okay? That is what an absorption spectrum actually is. Now it says the diagram below indicates some possible energy transitions made by atoms. Which one of the diagrams could result in the type of spectrum observed in 10.2.1? Okay, this is an easy question. So what we said was that this gas is at a low energy state because it's cold. When the blue light entered, it allowed, for example, the electrons in this atom to become more energetic. So they use the blue light energy to be able to become more excited. So they are able to jump up from lower energy levels to higher energy levels. So that would be this diagram, because here we can see that we're going from lower energy levels up to higher energy levels. Whereas in this diagram, we're going from high energy levels down to lower energy levels. Okay, so it would definitely be diagram B.